Welcome to The Explainer. Today, we're going to cut right through the buzzwords and demystify the complex math and control systems of industrial robots. This one is designed specifically for you, the info engineer. You know, it's so easy to look at a modern manufacturing floor and think it's all just run by artificial intelligence. But today, we're drawing a hard line between what makes a machine smart and what actually makes it precise. We're going to unpack the hidden engineering that keeps massive metal arms moving at blistering speeds without flying apart.
Here's our roadmap for today. We'll start with the hidden high-speed math, then cover how PID loops are the secret to stopping. After that, we'll talk about building the digital fence, defining smart versus precise, and finally, mastering the integration layer.
All right, let's kick things off with our first section, the hidden high-speed math running inside the robot's brain.
We're starting right at the microscopic core of robotic movement. It's really easy to just assume a robot moves the way we do, right? But every single time that arm pivots, the computer is actually solving massive, complex triangle equations in milliseconds. It is pure trigonometry. The controller doesn't just push the arm forward, it actively calculates the exact angles required for the shoulder, the elbow, and the wrist to coordinate their movements simultaneously. If even one of those angles is off by a fraction of a degree, the robot misses its target entirely.
This is where inverse kinematics, or IK, comes into play. If you want to move the end effector, which is just the technical name for the hand or tool at the end of the arm, to a specific point, IK calculates the geometry for the shoulder, elbow, and wrist all at once. You dictate the 3D destination, and the IK engine actually reverses the math to figure out exactly how much each specific joint needs to rotate across 6 independent axes or degrees of freedom to make that happen.
Picture a real-world SCARA robot manipulator, for example. The physical structure depends completely on these exact trigonometric calculations to deliver that extreme payload capacity and speed. This specific design is an absolute powerhouse for fast point-to-point applications. When it swings its arm to drive a screw or place a heavy component, it's relying entirely on that underlying mathematical model to maintain a repeatability deviation of just 0.01 millimeters.
And that mathematical foundation builds directly into differential kinematics. This is what translates minute adjustments in joint positions into precise speed and orientation. Because let's face it, it's not just about getting to the right spot, it's about how fast you get there and what angle you're holding when you arrive. The Jacobian datrix acts as a bridge here, predicting how a tiny change in one joint's speed will ripple through the entire arm and affect the velocity of the end effector.
Moving on to Section 2, PIB, which is absolutely the secret to stopping.
Now that we know how it moves, how does it stop without crashing? Getting a massive arm moving is really only half the battle. If an arm is flying toward a point, it has to slow down as it approaches, or it's going to crash. The secret sauce here is the PID controller. It uses a proportional response to gauge the current error magnitude, an integral calculation to clear out any tiny lingering drift, and a derivative calculation to predict the rate of change and dampen the force. This ensures the system stops smoothly and exactly on target instead of violently overshooting. Imagine the PID loop as this incredibly fast, anxious voice inside the motor's head constantly yelling, "Hey, you are moving too fast, slow down by 5%, now, 2% now, stop exactly here." It continuously measures the actual position against the set point, calculates the error, and adjusts the electrical current to the motors. Without this continuous real-time modulation, the immense inertial mass of the robot arm would literally tear itself and your factory apart.
Let's move to Section 3 and look at how we build the digital fence for safety and space.
Scaling up from the brakes to the physical world, we have to figure out how to keep these massive machines safely contained. An industrial robot generates hundreds of newtons of force and carries immense kinetic energy. Because of this, a robot operates strictly within a work envelope. Think of it as a programmed digital fence that the robot physically cannot cross. It is the absolute maximum reach mapped out in Cartesian space, and the system controllers will stop the machine dead in its tracks if a programming error tries to send the arm outside of this safe 3D zone. This digital fence isn't just a good idea. It is a codified engineering requirement to prevent all that kinetic energy from causing harm. ISO safety standards strictly mandate these integrations. ISO 1028, for instance, requires safety-rated soft axis limits. Integrating these systems also requires mandatory risk assessments for any modification, and specific standards like ISO 15066 dictate the highly unique safety protocols needed when humans share space with collaborative robots, or cobots. If a limit is breached, the safety system cuts power immediately, no exceptions.
That brings us to Section 4, Smart versus precise, and demystifying AI in factories.
This right here is a major industry misconception. We hear AI thrown around everywhere, and it's easy to assume your robotic arm is acting like a smart thinking brain. But we need to draw a stark contrast. AI is heuristic, meaning it guesses, it tries things, it operates based on probability. Factory robots, however, are strictly deterministic, meaning they follow a rigid, set mathematical path. The robotic arm is just executing those inverse kinematics and PID loops we just talked about. It does exactly what the math dictates, with absolute zero room for guesswork.
And that difference is crucial because AI lacks formally verifiable decision boundaries under all input conditions. We rely on deterministic systems for functional safety, leaving AI for predictive tasks like scheduling and maintenance. You simply cannot safety certify a system that might randomly decide to take a different path to optimize its swing. AI is fantastic for analyzing vibration sensors to tell you when a bearing might fail, but the physical swing of that robot arm must remain mathematically predictable at all times. You have to know where it will be at every millisecond. Finally, Section 5, Mastering the Integration Layer, out on the factory floor. In a real facility, absolutely none of this operates in isolation. The Programmable Logic Controller, or PLC, acts as the true grandmaster of the modern factory. It coordinates the robotic arm, the conveyor belt, the vision sensors, and the safety scanners all at once. The robot arm is just one player on the board. The PLC reads inputs from hundreds of sensors, executes the logic, and perfectly times the handoff between a moving conveyor and our mathematically precise robot arm, making sure production is fluid and continuous.
So, since you're managing these projects, here is a massive pro tip for process optimization. The secret to high factory output is not just going out and buying a faster robot. It's using the PLC to eliminate the arm's dwell time, that's its idle time, through perfect synchronization. If your robot finishes its lightning-fast movement but then just sits there waiting 2 seconds for the next part to arrive on the conveyor, that incredible speed is completely wasted. True optimization comes from tuning the entire closed-loop system so the robot is always moving and never waiting.
So, as you look at your own factory floors, I challenge you to really examine your control loops and integration points. Where can you transform precise math into real-world efficiency? We've seen how trigonometry, PID controllers, and deterministic logic make these machines incredibly powerful. But the real question is, how will you re-engineer your integration layer to orchestrate that power and minimize dwell time? Thanks for joining me for this explainer. Until next time, keep analyzing, keep optimizing, and keep building the future.